Printed circuit board. The motherboard is a stack of copper pathways pressed between layers of fiberglass. Every component on it is just talking to another component through those paths. That green coating on the outside protects those paths from oxidation and short circuits. Scratch through it while installing something and whatever that trace connected to stops working permanently. CPU socket. The CPU socket is the single most important mechanical component on your motherboard because it's the one that connects the processor to everything else. Without it, your CPU would need to be soldered directly onto the board, which is exactly what laptops do, and exactly why upgrading a laptop processor is basically impossible. There are two main designs. LGA, which stands for Land Grid Array, puts the pins on the motherboard and flat contact pads on the CPU. This is what Intel has used for years and what AMD switched to with their AM5 platform. The other design is PGA, Pin Grid Array, where the pins are on the CPU itself and the motherboard just has holes. AMD used PGA for its entire AM4 lineup covering Ryzen 1000 through 5000 series. The difference matters more than you'd think. With LGA, if you slip during installation, you bend pins on the motherboard. With PGA, you bend them on the processor. Either way, one bent pin in the wrong spot and the whole thing is dead. Intel's current LGA 1700 socket has 1700 of those pins packed into a space roughly the size of a matchbox. Every single one of them needs to make contact. So instead of just dropping a chip in and hoping for the best, modern sockets use a zero insertion force design. You place the CPU in, lower a metal retention plate, and a lever locks it all into place. No pressure required from your end during the drop, which is good because the margin for error on something with 1700 contact points is basically zero. Chipset. Two motherboards can use the exact same CPU, the exact same RAM, and still behave completely differently. That's the chipset. In the old days, this was literally a set of two chips. The North Bridge sat close to the CPU and handled the fast stuff like memory and graphics. The South Bridge handled everything slower, like USB ports, audio, and storage. Over time, the CPU got smart enough to handle memory and graphics communication on its own, which made the North Bridge unnecessary, so it got absorbed into the processor. What's left today is a single chip that Intel calls the Platform Controller Hub, and it handles everything the CPU doesn't want to deal with directly. That's why the chipset letter matters when you're buying a board. Take Intel's 700 series. A Z790 board gives you overclocking support, up to 28 PCIe lanes from the chipset, and a pile of USB and storage options. A B760 board uses the same socket, runs the same processors, but cuts the PCIe lanes roughly in half, drops overclocking entirely, and strips back the USB count. Same CPU, noticeably different board. So when someone says just get a cheaper motherboard, it doesn't matter, what they're really telling you is that they've never tried running 3 NVMe drives and a capture card on a budget chipset. It matters. It just matters quietly until the day it doesn't. DIMM slots. If you've ever put two RAM sticks into a motherboard side by side and wondered why your system felt slower than it should, you already know why this section exists. Those long, narrow slots next to the CPU socket are your DIMM slots, and the way you populate them changes how your memory performs. Most motherboards have 4 of them, arranged in 2 pairs for dual-channel memory. Instead of all your RAM data traveling down one 64-bit path to the CPU, dual-channel gives it 2 paths running simultaneously. That effectively doubles your memory bandwidth. But to activate it, you need to install your 2 sticks in the right slots, which is usually the 2nd and 4th slot from the CPU. Put them next to each other in slots 1 and 2, and you're running single channel without even knowing it. Your system will still boot, everything will look fine, and you'll just quietly lose a chunk of performance for no reason. One more thing worth knowing. DDR4 and DDR5 sticks are physically keyed differently, so a DDR5 board won't accept DDR4 modules. You can't force the wrong generation in, which is probably for the best. Voltage regulator module. Your power supply sends 12 volts to the motherboard. Your CPU needs about 1.2. If those 12 volts reach the processor directly, it would be dead before you finished your first boot. The VRM, or voltage regulator module, is the circuit that steps that voltage down and keeps it stable. It's not one component. It's a collection of MOSFETs, chokes, and capacitors arranged around the CPU socket, usually along the top and left edges of the board. Together, they form what are called power phases. Each phase takes turns delivering current to the processor in rapid pulses, and the more phases you have, the smoother and cooler that delivery gets. A board with 4 phases means each one handles a quarter of the workload. A board with 16 phases means each one barely breaks a sweat. This is where the spec sheets start playing games. You'll see boards advertised as 16 plus 2 phase power design, and that first number is the count dedicated to the CPU. But some manufacturers use phase doublers, which split one real phase into 2 separate circuits. You get better heat distribution, but not the tighter voltage control of actual independent phases. A board claiming 16 16 phases might only have 8 real ones with doublers doing the rest. The practical difference shows up under load. Say you drop a high-end processor into a budget board with a weak VRM, under a full workload, the CPU starts pulling serious current. The VRM can't keep up, it gets hot, voltage starts drooping, and the CPU throttles itself down to survive. You paid for a fast processor, and your motherboard is the reason it won't run at full speed. Nobody looks at the VRM when they're shopping for a board. They check the feature list, maybe glance at the price, and call it a day. Then 6 months later, they're on a forum asking why their CPU runs 10 degrees hotter than every benchmark they've seen online. PCIe slots. Your graphics card needs a direct, high-bandwidth line to the CPU, and the PCIe slot is what provides it. These are the horizontal slots running across your motherboard, and they come in different physical sizes, by 1, by 4, by 8, and by 16, where that number tells you how many data lanes the slot has. More lanes, more bandwidth. The by 16 slot is almost always the top one and connects directly to the CPU for the fastest possible link. That's where the GPU goes. The smaller by 1 and by 4 slots handle things like Wi-Fi cards, sound cards, and capture cards. Everything is backward compatible, so you can plug a by 1 card into a by 16 slot and it'll work fine. It just won't use the extra lanes. The part that trips people up is this. A board might have 2 full-length by 16 slots, but only the top one is actually wired with all 16 lanes. The second one could be running at by 4 or by 8 electrically, even though it looks identical. The physical slot size and the actual wiring don't always match, and manufacturers don't exactly put that in bold print on the box. So if you're planning to run 2 GPUs or a GPU plus a capture card, check the manual before you buy the board, not after. M2 slots. Before M2, if you wanted an SSD, you plugged it in with a SATA cable like a hard drive. It worked, but SATA tops out at around 550 megabytes per second, and modern NVMe drives can hit 7,000 or more. M2 slots are what made that jump possible. They're small horizontal connectors built directly into the motherboard that use PCIe lanes instead of the SATA bus, and they accept drives roughly the size of a stick of gum. The standard size is called 2280, which literally just means 22 millimeters wide and 80 millimeters long. You screw one end into a standoff and that's it, no cables, no brackets. The gotcha is that not every M2 slot supports NVMe. Some only run SATA, even though the drive physically fits. You plug in your fast NVMe drive, boot up, and the system doesn't even see it. The motherboard manual is the only way to know for sure which slot supports what. Power connectors. Your motherboard has 2 separate power inputs, and it won't boot without both of them. The big one is the 24-pin ATX connector, usually on the right edge of the board. This feeds power to the chipset, RAM, PCIe slots, fan headers, and basically everything that isn't the CPU. The CPU gets its own dedicated line through the 8-pin EPS connector tucked up in the top left corner. This delivers 12 volts to the VRM, which then steps it down to whatever the processor needs. High-end boards sometimes have 2 of these for overclocking headroom. The classic first build mistake is mixing up the 8-pin CPU cable with the 8-pin PCIe cable meant for graphics cards. They look almost identical. One splits into 4+4, the other into 6+2. Plugging the wrong one in is a fast way to have a very expensive, very bad day. SATA ports. SATA has been running at the same speed since 2009, 6 gigabits per second, which works out to roughly 750 megabytes per second in practice. In a world where everything else on the motherboard has doubled its bandwidth multiple times over, SATA just stayed exactly where it was. That said, it's still on every board. Those small L-shaped connectors along the right edge are where you plug in hard drives, 2.5-inch SATA SSDs, and optical drives if you still have one. Each port takes one cable and connects one device. The thing worth knowing is that some SATA ports share bandwidth with M2 slots. Pop an NVMe drive into certain M2 connectors and 1 or 2 SATA ports quietly disable themselves. It's not a defect, it's a design choice because the chipset only has so many PCIe lanes to go around, and the M2 slot and the SATA port are fighting over the same ones. 15 years at the same speed, and SATA still finds new ways to be complicated. BIOS, UEFI chip, and CMOS battery. Before your operating system even thinks about loading, something has to wake up the hardware and make sure everything is working. That's the BIOS, or on modern boards, UEFI. It's firmware stored on a small chip on the motherboard, and the very first thing it does when you hit the power button is run a self-test. It checks the CPU, the RAM, the storage drives, and if anything fails, it throws an error before Windows or Linux ever gets involved. UEFI replaced the old text-based BIOS with a graphical interface you can actually navigate with a mouse, along with faster boot times and and support for drives larger than 2 terabytes, but it's still doing the same fundamental job. There's one more thing worth knowing. When a new CPU generation launches, older motherboards often need a BIOS update before they'll even recognize the processor, which creates a problem. To update the BIOS, you need a working CPU, but the CPU you just bought won't boot until the BIOS is updated. Some boards solve this with a BIOS flashback feature, a dedicated button on the I/O panel that lets you flash the firmware from a USB drive with no CPU installed at all. If you're buying a new processor for an older board, check whether your board has this before it becomes your afternoon. Next to that chip, there's a small silver disc that looks like a watch battery, because that's exactly what it is. The CR2032 coin cell powers the CMOS, which stores your BIOS settings and keeps the system clock running while the PC is off. When it dies, and it will after about 5 to 10 years, your computer starts waking up thinking it's the year 2000 and forgetting every setting you've ever changed. The fix is a $3 battery from any drugstore. One of the cheapest repairs in all of computing, but endlessly confusing if you don't know it exists. Rear I/O panel. The rear I/O panel is the cluster of ports on the back of the motherboard that face out through the case. This is where all your external connections live. USB ports in various generations, an Ethernet jack, audio outputs, and if your CPU has integrated graphics, display outputs like HDMI or DisplayPort. Higher-end boards add extras like USB-C, Wi-Fi antenna connectors, and sometimes a BIOS flashback button. For years, the I/O panel came with a separate metal shield that you had to snap into the case before installing the motherboard. Everyone forgot it at least once, which meant pulling the entire board back out. It also had razor-sharp edges that would slice your fingers open during installation, which the PC building community treated as a rite of passage. Most modern boards now come with the shield pre-attached, quietly ending one of the most annoying traditions in computer assembly. Front panel headers. This is the part of every first build where someone ends up on Reddit at midnight asking why their power button doesn't work. Somewhere at the bottom of the motherboard, there's a cluster of tiny pins that nobody enjoys dealing with. These are the front panel headers, and they connect your case's power button, reset button, power LED, and hard drive activity LED to the board. The wires coming from your case are individually labeled things like PWR SW, HDD LED, and reset SW, and each one needs to go on a specific pair of pins in a specific orientation. The LEDs are polarity sensitive, so if you put them on backward, they just don't light up. There's no standard layout either. Every manufacturer arranges the pins slightly differently, so you're reading the motherboard manual with a flashlight in one hand and a pair of tweezers in the other, trying to push a connector the size of a fingernail onto a pin you can barely see. Some newer boards include an adapter block that combines all the individual wires into one plug. It's the kind of solution that makes you wonder why it took the industry 40 years to figure out. Every component on a motherboard exists because at some point, someone decided the processor shouldn't have to do that job alone. 4 decades of those decisions layered on top of each other. A $3 battery and a 1600 pin socket equally essential. Now you know what you're actually looking at.